The same thing with volume. We look around the classroom. What here has volume? They come up with all sorts of things like the rectangular pencil holders, the mouse's habitat, the tank has volume to it, and what makes something different, what is different from volume to surface area to area. And they come to the conclusion that volume, you can put things inside. Well, don't we need another dimension for that? Yes, what is that dimension? Well, it's the height or the depth of something. So we experience that, and then we talk about, well, volume. If area is measured in squares, volume is measured in cubes. Well, how about that garbage pail there that's a cylinder? Could that be measured in cubes? And most of the children don't think that it can be because it doesn't look rectangular, doesn't look cubic. But in fact, we still do measure it in cubes, so that's all discussed as well.
So it's very interesting that language matters a great deal. So when we say cubic centimeters, then they tend to think of a cube, and not just the abstract dimensions. So
that's right.
Again, it's paying attention to language matters a great deal.
So why does a ball roll? Why does a sphere roll? Does a sphere roll? Yes. How does it roll? It rolls in all directions, Ms. Migdal. Okay, well, how about a rectangular solid? How about this rectangular solid we have here? Does this roll? No. Well, what's preventing it from rolling? Well, its edges and its vertices. Oh, so which one would roll the most? How about a cone? Well, a cone has a face here, and a cylinder has two round faces and no vertices. That rolls too, but it doesn't roll like a sphere does. It rolls back and forth because I guess those two faces do something to it, whereas the sphere has no faces and has no vertices, and it has no edges, so it can roll in so we talk about that as well. So now they go into Model Maker, and they have their background in mathematics. They have their background with surface area. They have their background with volume, with all the different polygons, with all the different 3D figures. And now they're ready to attack the challenge head on. So we start them off with volume, and we say, okay, so how large, between the range that you were given, now you have free reign. Go in, decide what you're going to be using. But actually before that, I ask them to go in before they do the challenge, and they have to find each one of these 3D figures: the rectangular prism, the cone, the cylinder, the triangular prism or solid, the square-based pyramid, and the triangle-based pyramid, to give me a snapshot that they get how to make these on Model Maker and how to find the volume. And of course, they're so happy that they could find the volume by hitting
the properties.
The properties and preferences, and then they can find that it will give them the volume. They can take a breath from all the computation and calculations that they've been doing. But actually, I make them do both because I'm a bit of a hard nose with that.
And I noticed with the calculations that you like them to do it by longhand and not just use a calculator.
Yes. So I do make them actually do both, and have them check with Model Maker, and sometimes I'll give them a break. I'll say, well, out of the 4 shapes that you're doing, 2 I want you to show me all the computation, and if I feel it's a little unwieldy for them, and 2 you don't have to do the computation, as long as I can see that they get how to perform the calculations.
And that's great. And this is where we can have software remove some of the tedium of the calculations,
of
which there are a lot of calculations.
They now see, oh my goodness, we did the volume and we were so proud of ourselves. We got it within the range, and we love, and I think they have like 10 shapes, 10 3D shapes. They're so excited that these are going to print out, and all of a sudden they start doing the surface area, and they say, it's not fitting with the specs. It's just not in there. We're going to have to either decrease the volume, we're going to have to get rid of some 3D shapes here, we're going to have to make some trade-offs. And that is the job of an engineer. And that increases their ability to problem solve. I find it critical and crucial. And they have to let go, and they have to now readjust their ideas, which is to me, the most fascinating part of this. And they see, well, if I put this surface area and this surface area together, and this comes off now, I'm going to take away this one 3D shape totally, and that volume will remove that surface area, and now we can balance it out. And it's just amazing to watch them.
And that's fabulous. And looking at them not only balancing volume, but where surfaces meet, they subtract both surface areas and they become much more knowledgeable of what surface area is in this calculation.
True to real life, and just applied mathematics, perfectly applied. I am a stickler for it, but they must show evidence of their work, of their thinking, and again, if they just have numbers on a page, it's unacceptable. They have to show what each number represents, so that I know when I go back into this if it matches and if they're on target or not. They do work in teams. I had them work usually in teams of 3. I find that's a good number, especially if they're together on one computer. 4 may be too crowded. 3 is good, but yes, many times I've seen 2 would be on FabLab Maker and one person would be doing the computation because they were still trying to get something and I was working with them. Every child is accountable for their own design technology portfolio. Every student is accountable for their numbers and their work, but again, they can pair together and then come alone and work with me or work with a peer tutor, a peer helper. And they also peer assess each other as well. So.
And you have assessment guidelines to scaffold that.
That's correct. That's correct.
Great.
We have a rubric, and the students, just like if you were in a college course and you'd want to know what it takes to get an A before you start, usually the professor will give out a rubric to let you know what's an A or a B plus, or the same thing with, I believe, with students in elementary school or middle school or high school, that they really should have a rubric to let them know what it takes for them to get whatever they want to get on this. If a B is fine, this is what it takes. You're going to have to do A, B, and the rubric is very well spelled out for them for this specific design challenge. The program allows you to print out the image, and they have to prove that. This is one of their proofs that they're ready to go to start printing it out on the cardstock. Now, another roadblock that they find is, well, I wanted to make this figure like it was a torus or something very difficult, or a sphere or a dodecagon, and it becomes hard when it's printed out to put it together. So then they have to go back, modify, and take away certain 3D shapes that are too difficult for them to actually put together and recalculate. But they stay with it, and it's amazing. Spheres and toruses are very difficult, very challenging because of the constraints of the size of the paper, and the sphere and the torus come out small, and you need to have such precision to put them together. But they love the spheres and they love the toruses when they first start out. And the beautiful part of that is also how much surface area does the torus really take up when it's touching something else. And they use estimation skills for that, which is another perfect way to use. I mean, estimation is so important these days to really apply that. The reflection page, which reflects on the mathematics behind it, it also reflects on trade-offs, modifications, things like that. It appears to be towards the back of the packet, of the portfolio. But you really need to employ pieces of this in the middle part of this. When they are making the trade-offs, it's the time when the teacher has to say, okay, go to the reflection page and skip 3 or 4 pages. Reflect on this now, because you can't miss those opportunities where, oh, we can't use that torus, or oh my goodness, our volume is too large. We have to, now with the surface area, you have to catch that moment, then have them reflect right away, and that is really used throughout.
And so when you do that, you find that when they finish and they read what they wrote, they say, "Oh yeah, I remember that."
Yes, yes. I mean, they go back and forth, and you know, it's a really good skill for students to be able to do that anyway. We want them to do that in ELA, to go back, and then so I mean, it's a good skill, all around skill to do. So I find it very useful. The extension questions I use usually for the students who have completed the challenge before others, and we use the extension questions. This one is, how does the base area of an extruded figure relate to the volume of the extruded figure? And I keep it open-ended, and I find that we get a lot of different ways in which to tackle this, and then I have those different groups of kids that have done these extension questions get together and post their ideas, and then they brainstorm together ways in which they tackled it. For this piece, they have to choose two different shapes, because it's important for 3D shapes for me to be able to see if they can reflect back and look at commonalities among the 3D shapes that they've used, and look at differences as well. They truly are doing the work of engineers and mathematicians, and they truly feel that that's who they are. And when I interview them afterward and I ask them, what was this for you? And they say that, you know, first of all, I didn't realize that engineers are really mathematicians and mathematicians are really engineers, which is such an amazing statement for me, to see that they see the two as so interconnected. And that they said, and just the application, that we were able to use the math, that we now love math more, which, you know, there's many statements that I have recorded of students saying certain things. One student, a girl, when interviewed, had said that she wants to be an engineer when she gets older now, but she didn't realize, she's a lover of math, but she didn't realize the connection between the two. And I said, what was the most exciting mathematics for you? And she said it was dealing with the specifications and constraints. And I said, well, how is that mathematics? And she said, well, when I had to look at the surface area and see that, you know, these two faces touched, that made me decide that I had to change some of my specs. So it's lines like that that make me understand that having it done, doing it this way, even though the mathematics is pulled out, when they go back in and apply it, they see it as working together. That's
fabulous. Well, I'm sure, thank you so much for sharing what you've done in the classroom. And it's very exciting, as always, talking to you about these projects that we're working on.
It's my pleasure.